Today, let us discuss the spectra of angle modulated signals. Unlike the amplitude modulation, this angle modulation is non-linear. Angle modulation is non-linear. So the calculation of exact spectrum of angle modulated signals is not so easy, especially for an arbitrary message signal. But our job can be made easy if the message signal is assumed to be sinusoidal. That is, m of t is equal to am cos omega m into t. That is equation number 1. So what we are going to do is, instead of analyzing the angle modulation spectra for arbitrary message signal m of t, we are going to study the spectra in detail for sinusoidal message signals only. So from this special case, we will try to reach the frequency domain behavior of angle modulated signals and can be then generalized. Therefore, m of t is assumed to be sinusoidal, or we will say that a tone. So m of t can be written like this: am cos omega mt. We have seen in the previous class that the instantaneous phase deviation phi of t is equal to kp into am cos omega mt this is equation number 2, and this is for phase modulation. And for frequency modulation, phi of t is equal to kf into integral minus infinity to t m of t t. Sorry, m of t dt for f, or we can write phi of t is equal to kf into integral minus infinity to t. M of t can be written as am cos omega mt t. On integrating, we will get phi of t is equal to kf into am divided by omega m into sin omega mt. Here we assume that phi of minus infinity to be 0. Let this be equation number 3. Therefore, for FM, the modulated signal can be written as xt is equal to a cos omega ct plus phi of t, and that phi of t is replaced by this equation. So x of t is equal to a cos omega ct plus kf into am by omega m into sin omega m into t, or x of t is equal to a cos omega ct plus beta into sin omega m into t, where beta is equal to kf into am by omega m and is known as a modulation index. So the parameter beta, that is modulation index, it represents the maximum deviation or maximum phase deviation produced by that modulating tone. Now for PM, for phase modulation, now let this be equation number 4. For phase modulation, that x of t can be written as x of t is equal to a cos omega ct plus phi of t, or x of t is equal to a cos omega ct plus that phi of t is replaced by for frequency, sorry, for phase modulation, that phi of t is here from equation number 2. We can write this phi of t as kp into am cos omega mt. This kp into am is replaced by beta, so x of t is equal to a cos omega ct plus beta into cos omega m into t. Let it be equation number 5, where beta is equal to kp into am, the modulation index for phase modulation. Now let us take the case of frequency modulation, that is equation number 4, which can be written, this equation, equation number 4, which can be written in the complex form as x of t is equal to a into real part of e raised to j omega ct into e raised to j beta sin omega m into t. So equation number 4 is rewritten in the complex form as a into real part of e raised to j omega ct e raised to j beta sin omega mt. Let it be equation number 6. Here in e raised to j beta sin omega mt, this sin omega mt is a periodic function. So this e raised to j beta sin omega mt is also periodic. With the period Tm is equal to 2 pi by omega m. So let us write the Fourier series expansion for e raised to j beta sin omega mt, and let this function be f of t. Therefore, f of t can be written as f of t is equal to sigma n is equal to minus infinity to infinity Cn into e raised to j n omega m. Here the total period is Tm is equal to 2 pi by omega m, which is divided from minus pi by omega m to plus pi by omega m. So the coefficient of Fourier series can be written as Cn is equal to 1 by t, or the reciprocal of time period, that is omega m by 2 pi into integral minus pi by omega m to plus pi by omega m e raised to j beta sin omega mt into e raised to minus jn omega mt dt. Now let this omega m into t with theta. We are giving a dummy variable theta to omega m into t, so that Cn can be written as Cn is equal to 1 by 2 pi into integral. The limit is changed to minus pi to pi because the integrating variable here it is theta, the dummy variable. So e raised to j into beta sine theta minus n theta into d theta. That omega m into dt is replaced by d theta. And this function, that is 1 by 2 pi into integral minus pi to pi e raised to j into beta sine theta minus n theta d theta, is the Bessel function of first kind. So we can write Cn as Jn beta, that is Bessel function of first kind. So let this be equation number 7. And these values of this Bessel function for different values of beta are documented, and they are readily available in the form of tables, which I will show you later. Now let us come back to our equation number 6 above. This one, this equation. So equation number 6 can be replaced by x of t is equal to a into real part of e raised to j omega ct into that Fourier series expansion can be written as sigma n is equal to minus infinity to infinity Cn e raised to Jn omega m into t, or is equal to a into a real part of this sigma n is equal to minus infinity to infinity Jn beta into e raised to j omega ct into e raised to Jn omega m into t, or x of t is equal to a into real part of sigma n is equal to minus infinity to infinity Jn beta e raised to j into omega c plus n omega m into t, or x of t is equal to a into sigma n is equal to minus infinity to infinity Jn beta cos omega c plus n omega m. Let this be equation number 8. Here we have taken that real part in this equation. We have taken that real part, so that you will get x of t as a into sigma n is equal to minus infinity to infinity Jn beta cos omega c plus n omega m t. This we have obtained a series expansion for FM, and from this equation the spectrum of FM signal can be represented easily. Now let us see that spectral properties. Now, here in this expression, that is expression number 8, omega m is the frequency of that modulating signal. That is this one. Omega 1 is the frequency of that modulating signal, and omega c is the carrier frequency. Let us recollect the frequency components in amplitude modulation. So in amplitude modulation, the frequency components were Fc, that is the carrier frequency, then the upper sideband frequency Fc plus FM, and the lower sideband frequency Fc minus FM. This was the case in the amplitude modulation. But here, in the case of FM, see this n, that is this n varies from minus infinity to plus infinity, so that we can have a carrier frequency, that is Fc. So in FM, we have a carrier frequency Fc and an infinite number of sidebands at frequencies Fc plus or minus n into FM, where n varies from 1, 2, 3, etc. So here we have infinite number of sidebands. Theoretically speaking, we have infinite number of sidebands, because the frequency here is omega c plus n omega m t. That is, n varies from minus infinity to infinity, so that we have infinite number of sidebands. Thus, here also we can have two sidebands, one set of frequency components lying above that carrier frequency Fc, such as Fc plus FM, Fc plus 2 FM, Fc plus 3 FM, etc. Okay, so these are the upper sideband frequencies, and the other set of frequencies lying below the carrier frequency are Fc minus FM, Fc minus 2 FM, Fc minus 3 FM, etc. These are the lower sideband frequencies. So the sidebands occupy large frequency domain. So theoretically, it extends up to infinity. So theoretically, the bandwidth is also infinity. This table shows the values of Bessel functions for different values of n and beta, and the second figure shows the frequency modulated spectrum for a value beta is equal to 5, that is modulation index 5. Before discussing that spectrum, let us recollect an important property of the Bessel function, that is Jn beta is equal to -1 the whole raised to j minus n beta. This is the relation between the Bessel function of order n and the Bessel function of order minus n. So this can also be written as Jn of beta is equal to j minus n beta for n even, that is minus a minus n beta for n odd. So this means that j on beta and j minus on beta, that is n is equal n is odd, they have opposite signs. But j2 beta and j minus 2 beta have the same sign since n is even, and so on. In this spectrum, the point corresponding to n is equal to 0, that is here, that point corresponding to n is equal to 0 denotes that frequency Fc. Here in this table, here it is beta is equal to 5 and n is equal to 0. Then you can see the value as minus 0.178. That's why this FC is plotted downward. Now, you need not worry about the values of that relative amplitudes because that relative amplitude of spectral components depends on the value J and beta. So it's an important point you have to remember. The relative amplitudes of spectral components depend on the value J and beta. Now, here this J1 beta denotes the frequency component Fc plus Fm. Here also, when beta is equal to 5 and n is equal to 1, the value is minus 0.32. That is, this Fc plus Fm is plotted downward. Now, J minus 1 beta, that is this one, it corresponds to a frequency of Fc minus Fm. And J2 beta, it denotes a frequency of this one, Fc plus 2 Fm. And J minus 2 beta, this one, it corresponds to a frequency of Fc minus 2 Fm, and so on. Here we see that J1 beta and J minus 1 beta are of opposite signs. That is, this one and this one. They are of opposite signs. That is, when n is equal to odd, the frequencies corresponding to J and beta and J minus and beta are of opposite signs. It is also seen in the case of J3 beta and minus J3 beta. J3 beta and J minus 3 beta are of opposite signs. If n is even, this J and beta and J minus and beta are same sign. Here you can see that J2 beta and J minus 2 beta are of same sign. So here we can see a large number of sidebands, and hence this is known as wideband frequency modulation. Wideband frequency modulation. So the phase relationship between the sideband components is such that the odd order lower bands are reversed in phase. Here you can see that lower sidebands. These all are the lower sidebands. This one, this one, this one. Here also, here in all these cases, we can see that that sideband components are reversed in phase. So that is the phase relationship between the sideband components. So the phase relationship between the sideband components is such that the odd order lower sidebands are reversed in phase. So that's an important point. The odd order lower sidebands are reversed in phase. Also, a large value of modulation index beta indicates that the bandwidth is large, since there are many sidebands. Here also you can see many sidebands. So when beta is large, the bandwidth is large. So next point is when beta is large, bandwidth is large. since we are having so many sidebands. Now let us recollect another important property of this Bessel function. That is when the modulation index of beta is very much less than 1. That is the argument of that Bessel function is very much less than 1. Then that J0 beta term becomes dominant. And the value of J0 beta is approximately equal to 1. And that of J1 beta is approximately equal to beta by 2. And that Jn beta is approximately equal to 0 for n is greater than or equal to 2. So we have already seen that the number of significant spectral components is a function of beta. So the number of spectral components is a function of beta. So when beta is very much less than 1, it is seen that only J0 beta and J1 beta functions are significant. So the spectrum contains the carrier corresponding to J0 beta. So FC corresponding to J0 beta, and this FC plus FM corresponding to J1 beta, and FC minus FM corresponding to J minus 1 beta. This is very similar to that of amplitude modulation spectrum that we have seen earlier, except that phase reversal of lower sideband component. There is no phase reversal for the lower sideband component in amplitude modulation, but in frequency modulation, we have seen that the lower sideband components undergo the phase reversal. So this type of angle modulation is called narrowband angle modulation. So it is a narrowband and angle modulation. So these are the spectral properties. So in the case of FM, theoretically we can have infinite number of sidebands, so the bandwidth will be infinity. Now that relative amplitudes of that frequency components depend on the value of this Bessel function. Normally we get a wideband frequency modulation spectrum for beta is if the value of beta is large, and the bandwidth will also be large. And the odd order lower sidebands are reversed in phase. Now the number of spectral components depends on the value of that modulation index. If beta is very much less than 1, we will get only 2 sidebands, that is upper and lower sidebands, and it is called narrowband angle modulation. Now in the next class we will discuss the power and the bandwidth of FM signals. Thank you.